Jeez, it's kind of dark in here. If only we had Have you guys ever wanted to build your own hologram?
Execute Order 66.
No, not that kind of hologram. This kind. Well, we did too. And that's why we set out to create the hologram. So for our project, we had $600 and 14 weeks to design a fully functioning hologram. To approach this problem, we decided to split our workload into three primary subsections. We had the software stack, the hardware stack, and the mechanical stack. Each three of these sections would need to work in parallel in order for us to have a fully functioning system. At a high level, we had a power supply controlling our three logic units: the Arduino Uno, the Jetson or Nano, and the Raspberry Pi. The Arduino was primarily there to control the speed of our motor.
For our software architecture, we mainly split up into two nodes, which is first the Jetson or Nano, which does more of the computation heavy stuff. And then on the actual spinning mechanism, we have a Raspberry Pi 02W that does the actual display driving, but none of the really complex math stuff. So starting from the Jetson side, we actually get input from our webcam, and that goes through an entire computer vision pipeline where we kind of just take snapshots and feed those into a media pipe machine learning model. And we kind of get extracted hand landmark positions that tell us where all the fingers are. From that information, we can kind of detect if there's any gestures going on or generally where the user's hand is located before trying to actually change that and translate it into some form of interaction for each application. Once the application kind of renders itself and figures out what the state of the 3D state looks like, then we can take 2D slices of what the LED panels should be displaying and kind of compress that data and send it over the Wi-Fi network using UDP. Then the Raspberry Pi will receive that data and kind of store it in a big buffer so it knows throughout a full rotation what kind of data should be displayed. And then the way it figures out when to display that information is by using a Hall effect sensor that triggers once each rotation, and that can allow us to kind of estimate how fast our mechanism is spinning and estimate when we should display each slice as we're rotating. And for the actual display driving, instead of using a library, we ended up opting for our own custom DMA driver, which is a little bit more complex, and we had to make some compromises because we can't display as much color, but it happens to be orders of magnitude faster than any library.
For our actual electrical hardware system, we had a 12-volt power supply unit, which was capable of supplying 350 watts. Selected this power supply unit specifically because it met our needs and actually exceeded the maximum amount of power draw from our system. We expected that at worst case, our system would draw at most 170 watts. And since our power supply unit can comfortably supply 350 watts, we should never be meeting our power constraint, even if our LEDs were operating at full power. Our power supply unit was powering both our Jetson, as well as the motor, and the LED display. Since our power supply unit supplied 12 volts and our Raspberry Pi and displays function on 5 volts, we needed to get a buck converter in order to properly step down the voltage to a level that is accessible for the rest of our system. Unexpectedly, or maybe expectedly, for 3 ECU majors, the step that came a little less intuitively to us was the mechanical assembly of our entire system. We had our motor, which was connected to the primary shaft via a belt, which was attached to each of our 3D printed gears. And the gears were then attached to the primary shaft, which spun the LED displays. So you can see here, this is how we originally planned to assemble our hologram. We had a 2-layered system with the motor and the actual gear located on the second layer. and our slip ring located on the third layer. And so our initial goal for this project was to achieve a frame rate of 30 frames per second, because we were thinking that similar to monitors, it would need 30 frames in order to have a smooth display. Since we have two displays, we did the math and figured out that this meant that our display should be spinning at approximately 900 rotations per minute. We wanted our system latency to be around 200 milliseconds. So within this time frame, lag should be pretty much undetectable for the most part. And our target weight for the system was around like 5 or 10 pounds, nothing too heavy. And since we had our theoretical plans ready, it was time to start building. Not enough power?
I feel good. I knew that I wouldn't. I feel good. I knew that I wouldn't. So good.
And so after many hours of presentations and too many Gantt charts, I present to you the hologram.
I couldn't wait for you to come and clear the cupboard. But now you're gonna leave with nothing but a sign. Another evening I'll be sitting reading in between your lines, because I miss you all the time. So get away, another way to feel what you do. Want yourself to know and let yourself go. You know you do lose your self-control. There's snow with the rainbow. Turn away, another way to be where you do want yourself to go. Let yourself go. Is that
So here's how the hologram looks in its full form. As you can see, we stuck to our general design that we had thought of prior to manufacturing. A lot of the system is very similar. We went with the 2-compartment system with the gear in the middle compartment, and our slip ring and power supply on the bottom. The chassis that we designed was actually one of the many issues that we ran into when working on this project. I know it looked like it went very smoothly, and it seems like a montage can fix everything and create anything you want, but for example, we had to redesign the chassis because it wouldn't fit the slip ring. A lot of our mechanical components weren't fitting perfectly, and so we ended up 3D printing a lot of clamps in order to connect to our shaft. In the end, we were operating at around 300 rotations per minute, which was around a third of what we had initially set as our target. As a result, our FPS also dropped to around 10 FPS. Our system latency we tested was around 500 milliseconds, but it didn't really make a big difference on the application since we didn't have any real-time applications. Our final weight came out to around 10 to 15 pounds. Although we didn't hit all of the targets that we had initially set out to hit, I would consider our capstone project a big success since it taught us a lot about the engineering design process and taught us a lot of valuable skills and experiences that we'll undoubtedly use in the future.